Good afternoon, everyone. We'll get started. We have two talks in this session. The first one is by Professor Nicola on Cuprate Twistronics towards a new generation of quantum hardware. So over to you, Nicola.
Okay. Thank you to everybody for being here, and thank you especially to the organizer for inviting me from this long way from home, let's say. And in this talk, I will try to dare, okay, to show you that in principle, cuprates, Twistronics can be useful. So I use many subordination sentences before, but this is my hope. And so I work at the Leibniz Institute for Solid State Material Research and at the University of Naples Federico II, the Department of Physics. And the group is made by many different people from different nationalities. And as you can see, many of them have contributed also to the work that I'm going to speak about, especially the students Tommaso, Miki, Sanas, Yejin. And also after me, there will be also Golam speaking, so I a little bit advertise so all the members of the group, and I also the funding sources that made this work possible, the European Research Council, DFG, PIAD, and TerraQuant. So, of course, this work has been made in the course of many years, I'd say, and some of the current main collaborators are shown here, and some of them are in Germany, in Dresden, in Italy, and internationally. And so, well, I would like to thank them all, and they are very important in this story. So, there are experimentalists, theorists, and crystal grower, and this. So when we speak about, let's say, qubits, we always think about an idealization, right, of two states, right, like in an atom, so two discrete energy states. So you have a strong idealization, right? You can make a little bit more complex idealization, starting to speak about an harmonic oscillator, physical circuit model, but at the end of the story, you have to deal with a physical layout. So there is a long way to go from the idealization to the physical reality, right? And what happens in between is one of the biggest problems today in physics, how to have your physical ideality actually in a physical layout. To show how this is actually important, I want to take the example of the Josephson effect, which is an effect that is at the core of many of the superconducting quantum technologies, right? The Josephson effect starts with very simple equations, right, which has been described by Brian Josephson, right? And he speaks about a superconductor, basically a barrier, and a superconductor where the wave function can interfere. So now, if you realize an array of Josephson junction, for example, by making an anti-dots array on niobium, you do see that if you measure the differential conductance, the differential resistance as a function of magnetic field, you will see minima and maxima in this as a function of the current. If you repeat the same experiment, more or less, changing the technology, an array of Josephson junction made of niobium, right? What you do see is that you will see this minima to maxima, but the quality of the data will be improving so much more that you will be able to apply statistical physics to measure critical phase transitions in the non-equilibrium vortex dynamics of the system. So what I'm going to say is that even though the principles are the same, right, depending on how you can reduce the detrimental disorder, you can observe the effect, you can understand new physical law. So you get closer to what is the physical idealization of the system. Now, in the meantime, there was a revolution in material science we call Twistronics, where 2D materials are posed on top of each other with a twist angle, right? And this has given us the unprecedented tunability on the correlated physics, superconductivity, and topological matter. At that time, I was wondering myself, okay, what about cuprates, right? So, because most of these works were done at the beginning with graphene, and then recently on TMDCs. So what about the cuprates? Well, cuprates are interesting because are materials that still nowadays show an inexplicable macroscopic quantum state. And the twisted cuprate structures is also a very old field. It's actually older than the twisted graphene. Were proposed for exploring new physics already by Manfred Sigrist in 1998. Now, why is not so famous? It's not so famous because cuprates are very complex material. And you can see that if you consider the only cuprate that is a van der Waals material, which is the bisco, this bisco has many, many chemical elements. So there is bismuth oxide, strontium oxide, copper oxide, calcium. There is a van der Waals gap. It is already a two-dimensional material in its bulk form, and it's the fact that it's already a two-dimensional material in this bulk form that makes it van der Waals. In fact, when I started to work on this, somebody asked me why you want to make something that is 2D more 2D. And I didn't have an answer at that time. Not yet today, I should say. But then what you can see here, however, is that complexity is inherent when you want to create macroscopic quantum states that are resilient to high temperature. So you cannot find an 100 Kelvin superconductor if you have a two-element system. You need to go to high-element system to have the hope to find an higher temperature superconductor. So this means that even if you had a room temperature superconductor, this probably will be extremely complex. And before you understand how to integrate that complexity into a device, it will pass many, 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 many years, right? Because still nowadays we have difficulties with the bisco, which is only 5-element compound, right? Why it's so complex? Well, bisco has a very special superlattice modulation, which is has a wavy nature, right? A wavy nature, which compensate all the internal chemical pressures between the atomic layers on top of each other. Then on top of that, the oxygen that compose the non-stoichiometric composition of the material that gives the superconductivity are not randomly distributed. Apical oxygen are disposed in some places where the oxygen interstitials near the strontium oxide are not, and where the oxygen interstitials near the bismuth oxide are not, which means that the overall electronic structure at the end that you can measure with STM, for example, is really dependent on this specific disposition and on the wave modulation. Now, we don't understand really what they do because we don't have a theory for high temperature superconductivity, not even for the normal state. But on the other hand, we must acknowledge that they do something and they must be important. So now I was studying oxygen interstitials for a very long time, and actually I was studying on the lump copper oxide, was mentioned before. And I was using micro X-ray diffraction, and what I was discovering is that oxygen interstitials in a cuprate not only are doped into the system, but they form ordered structure. So there is a K-space ordering of this oxygen, which forms kind of stripes. And these stripes gets more ordered or less ordered depending on if you warm the sample above 300 Kelvin, so the stripes gets more disordered. And if you cool down the stripes, they will remain disordered. So these oxygen interstitials will not be ordered, which means that not that the oxygen have escaped your material, the oxygen are inside your material, but they are not ordered anymore. And this changes the critical temperature of your system. So somehow it's like that you change this fractal structure of oxygen ordering to a less fractal structure, and this changes the critical temperature of your system. So what I discovered was that when it's disordered, the oxygen ordering, if you apply X-ray light for several hours, you start to rebuild up this oxygen ordering. And if you cool down the sample again, you will restore the optimal TC. This is what tells, why is it so important, this story, for the story that I'm going to tell you? It's important because oxygen intensity order can be tuned with conic exposition of X-ray light in between 200 and 300 Kelvin, which means that below 200 Kelvin, the oxygen interstitials are frozen. So the chemistry is completely frozen, nothing happens, it's dead, the system. And this is very important. So people were starting to use X-rays to realize Josephson junction, but the story is that they were not changing the local oxygen ordering, but they were actually depleting the oxygen from the material. So the oxygen were escaping. The quality of the Josephson junction, therefore, even though the idea is great, the quality of Josephson junction, the critical current was pretty low, and the control on the TC was very small. So in the meantime, of course, people started to stack this crystal of cuprates on top of each other. The first experiments goes to Lee in 1999, where they were putting flakes on top of each other, or bulk crystals. Now, then later on artificial whisker junction, a natural whisker junction, X-ray the flakes more recently. All of they have in common is that here the two flakes or the two crystals on top of each other were forming an insulating barrier. But the superconductivity was restored after applying a very high temperature, 500 Celsius, 800 Celsius, to have the oxygen, let's say, repopulate the interface. And this gives the superconductivity. But unfortunately, this, let's say, what they measured was that there were no angular dependence on the critical current density as a function of the angle. Now, this is kind of surprising because except Takano in 2012, the overall majority of in the last 25 years of reports showed there were no angular dependence in these materials. But they all have in common that the temperature at which the interface was formed is extremely high. Now, this is really against the oxygen because they are very light elements. They like to move. And when they move, they create cracks and vacancies and defects. And you want to avoid that. So the challenge for me was, okay, this is wrong in my opinion. So we need to find a technique that preserves this essential heterogeneities, which you can see here in terms of oxygen, the interstitial ordering in the lanthanum copper oxide, for example, of a micron scale. So we have to preserve this essential heterogeneities while we fabricate the heterostructure. Now, if you look at the van der Waals technologies of the time, you could use polymer like PPC or PC, which have a glass temperature of transition of 90 or 200 Celsius for making the stacking. So this means that you have to warm up, you have to liquefy the polymer and then freeze and then stack and so on and so forth. But the oxygen are mobile below, above this temperature, which 200 Kelvin, minus 73 Celsius. So the challenge was to find a stacking methodology which works below this temperature. Now, of course, this was a long road. At the beginning, working with Bisco was done by Guy Novoselov, stamping with Scotch tape on a substrate, the Bisco crystals. You can see a picture. And then in 2019, people started to isolate this crystal by, first of all, recognizing the fact that you do not want to have water molecules into the system contaminating your material. You want to create smart ways to make the contacts. So for example, by not directly putting and spinning polymers on top of that. So you want to avoid at all cost, let's say, at all cost, you want to avoid any contaminants. And this led that you could start to see that the superconductivity was preserved around 290 Kelvin for an optimally doped sample. And you can see also the superconductivity fluctuation increasing depending on the thickness. And this was an important achievement in these two works. To give an idea of how sensitive these materials are, I want to just show you one very quick way that this is a little bit long, but we did an experiment, a non-X-ray diffraction at Brookhaven National Lab using a 100 nanometer X-ray beam. And if you use diffraction, you can see two peaks in the Bisco that we call long-range order and short-range order. These two peaks, you can map the wave vector of the two peaks in real space, like we did for the oxygen interstitial ordering. Now, if you, 0 means that it's basically 0.21 B star, is the average wave vector of this peak. And then how this average move out across space. And now you see that for a bulk crystal, there is basically a Gaussian distribution. This green line is basically resolution limited. So with 1 over 1,000 change. So this basically, the wave vector of the supermodulation of the Bisco doesn't change for 1 over 1,000. So it's very, very constant. It's remarkably constant. But as soon as you exfoliate a flake, and if you do that at room temperature, even in a glove box, you start to see that this Gaussian distribution, even though the system is 90 Kelvin superconductor at the end, you see some change, some strain, okay? So you see that even the simple process of exfoliating in a very protected environment, room temperature, the system creates some change respect to your bulk crystal. Okay, but we solved this problem, and now we have another methodology that can create ultra-clean twisted cuprate interfaces. Now, the idea is a mix between luck and insights, of course, and starts with the idea that PDMS turns out to become like a Scotch tape at very low temperature. And around the minus 90 Celsius, we basically exfoliated the crystals, we tear in two pieces, and in less than 1 minute, maybe because of my Italian temperament, we have to restack the two crystals on top of each other. So instead of 7 hours, like in graphene, when you try to remove the bar, we do in less than 1 minute. Okay, and this was, I remember the time I did this, I was kind of angry. But anyway, so the point is that the top twisted layer, you can see quite nicely, in a very nice way, the atoms modulating themselves, the interface, and the bottom layer. Of course, the symmetry is different because you are seeing a cross-section, and this is around 45 degrees. So the idea is that shows in these three papers is that we can now engineer complexity, topological, and strongly weighted physics in one system in a wide range of temperature. Now, this is in the lab that we have in Dresden, where we have performed some of these experiments. And the important aspect is that the interfaces are realized with a dew point of the temperature of the water at minus 100 Celsius. So basically what I do is to take a microscope, see a cold stage, and check if at some point there is condensation of water as soon as I cool down the temperature. So if there is no condensation of water around minus 100 Celsius, means that the atmosphere is quite good. And this takes 7-8 months to get in a glove box system. Now, how the recipe works. So basically, you have the biscuit on the substrate, the PDMS, you are minus 90, you exfoliate, you remove the flake, you restack, and in less than 1 minute, at minus 30 Celsius, the PDMS become less sticky, and you can release the flake. Depending if you are rich or not, and if you have a UHV evaporator, right, with an evaporator at 10 minus 8 torr, you have less molecule of water, so you can directly go on this step. But if you have a smaller evaporator with a lower vacuum, like 10 minus 6, then it's better to put an encapsulation layer, right? In this case, we put boron nitride. Then you go to this step. So the very interesting thing that I didn't know when I started these experiments was that PDMS has a glass transition at minus 120 Celsius. So somehow, and I don't understand why, the PDMS become more liquidish, right, instead of more solidish, once you lower the temperature instead of once you warm the temperature. All the others have a glass transition around this temperature. So now, again, to show how sensitive these materials are and why there were 25 years of problems to understand and finding a consensus, I want to show you this other example. So you have two visco flakes on top of each other at 0 angle. So the twist angle is basically the same as it should be if they were a bulk crystal. And now in one case, we create electrical contacts here also, and in another case, we put electrical contacts and the encapsulation. Right, in both cases, the TC of the junction, so the current goes through the junction, you measure the voltage drop across the junction, is 90 Kelvin. So from the point of view of the bulk crystal, it seems pretty good. The point is that if you look at the AV characteristic, in one case, at 0 angle, you see the critical current extremely small. In another case, you see the critical current as close as they should be when you speak about intrinsic Josephson junction in a bulk crystal, which is around 1.1, 1.2 kilooampere per centimeter square. Now, you can do this experiment, change the angle. You can see that this black area basically constitutes your critical current, your JC, density critical current. And as soon as you start to change the angle, you start to see that this dark area becomes smaller and smaller. And you can see that this has a trend that follows the cos to phi or cos to theta, which has a D-wave angular dependence. Now, you can repeat this experiment many, many times. You can give also different configuration of electrical contacts. In this case, we were using a higher vacuum pressure, like 10 minus 8, right? So we didn't need an encapsulation. And you can put electrical contact on top, on bottom, so that the current flows through the interface. You see, for these 60 samples, more or less, you have the same, you have a distribution of 2.8 Kelvin. The critical current shows under damped junction, this shows a very, very big hysteresis, and the critical current of 1.2, more or less, close to for the 0 angle degrees. But when you start to change the angle, you have this ICRN that started to change, flows near close to phi. Doesn't go to 0 at 45 degrees, and there is a reason for that, and of course return back. So at least here we can say that we have some incoherent tunneling that should come from this dependence. Now, what about coherent tunneling? Do we have coherent tunneling between the wave? Well, if you look at the temperature dependence of the dynamic resistance for the different angle, you will see that you will go from some sort of almost monotonic, like you may expect from monotonic dependence as a function of temperature once you get close to 90, but to a non-monotonic, like you see this Tm here, a non-monotonic dependence which you have at intermediate angle. So this can be explained, and of course this non-monotonic dependence vanishes once you get to 45 degrees. So you can get negative and positive contribution to the AC depending on where you are in the nodal region with respect to each other, because you have also a phase. You don't only have an orbital, right, or the parameter, but each orbital have a phase. And this matters, right? And this matters especially at intermediate angle. So an additional proof of the D-wave symmetry comes from a recent analysis that has been done by Talantsev, is that basically you can generate the Ambegaukar-Baratov relationship has been assumed for many, many years, always with a Wiki clamping and S wave. So assuming that it is a S wave, but if you actually introduce the wave component, you can perfectly fit the data experimentally that I showed you before. And this provides further evidence that you have a D-wave symmetry for the C-axis superconducting gap in the twisted biscuit junction. Now, if you have two order parameters, right? So if you have one layer that is the flake below, 30, 40 nanometer, we are talking about flake, not monolayer, 30, 40 nanometer more or less on the average. On below, you expect this order parameter and another order parameter. So ideally, you may expect this order parameter to appear at the interface of your two crystals. So if that is true, you have the advantage that second order mechanisms are predicted to support an interfacial superconductivity with a doubly degenerate Josephson energy, which is due to this kind of order, new parameter, this new order parameter artificially created. Right? Now, if that is true, you should have at around 45 degrees a purely second harmonic contribution to the Cooper pair tunneling, which means that you should have a critical current here that is not zero, that is given purely by the second harmonics. Of course, you have a second harmonic, but you will have a first harmonic, and as soon as you go back, so to lower twist angle, the first harmonic contribution becomes stronger, and the second harmonic contribution vanishes. But there is a special region of coexistence, right? And a region where the second harmonic is completely dominant. In any case, it has been predicted that in a region of angle close to 45 degrees, even topological superconductivity could be measured. Now, what about the second harmonics, first of all? Right? So if you apply radio frequencies, right, at around 48 gigahertz for a sample that is around 43.7 degrees, you see that you have integer Shapiro steps, as you may expect if only a first order Josephson junction contribution to the harmonics was present. But however, if you get, as soon as you get closer to 45 degrees, you start to see not only the first order contribution, but also second harmonic, a fractional Shapiro steps here. And this is not due to interfacial roughness of the interface or angular disorder, special angular disorder, because given that we have a thick flake, we can actually measure it. And we can measure it using convergent beam electron diffraction. And we do see that the upper bound that we can put to the angular disorder is 0.2. If you had these fractional Shapiro steps coming from something else that is not a second harmonic contribution, this angular upper bound should be above 0.5. So we are well below that number. Now, if we measure the Fraunhofer pattern, you can start to see that there is a region close to 45, in this case it's 44.9, where the second harmonic is mostly dominant, and this is seen by the shape of the Fraunhofer pattern, which started to instead change as soon as you get a little bit far away, around 46.3, where you see the two harmonics intertwined together. So you start to see a very long oscillation and a faster oscillation here. Right. Now, if you have a region where a second harmonic is dominant, another region where the first and the second harmonic are coexistent, and another region where the first harmonic is dominant, you can also start to think about that there will be maybe a region where you have spontaneous time-broken states. And this is for checking that, so that you have actually a region where you have two valleys, you can, for example, measure macroscopic quantum tunneling or switching current probability distribution and apply different protocols on which you prepare your phase in one of the two well, as you can see, of your potential, giving one polarization or the other depending on the current in which polarization you apply the current. And then you can see you can have this potential with the phase here, or this potential with the phase here, or this potential with the phase here, or this potential with the phase there. And then you prepare your particles in one of these valleys, and then you measure. And this is basically what is written here. So you prepare the particle, you measure. You prepare the particle, you measure. You prepare the particle, you measure, and so on and so forth. You measure 10,000 times. You do a statistical analysis. You make sure there are no magnetic field in your lab. Because if there is even a small magnetic field, you will see everywhere. So what happens is that at high temperature for angles that are close to 40, 42, if I remember correctly, you start to see that the four protocols that we show 4 different states. Okay? So you see that you have a splitting of the different distribution, right? Below 54 or below temperature, which goes in 4 different histograms, right? And this kind of gap starts to open a larger enough. So you basically get 4 critical currents. And so 4 places where your phase can sit, right? And this can be summarized in this way. So if you repeat these experiments for all the angle that you have, what you start to see is that for low angle, right, you do not see any kind of diode effect. So you do not see any splitting, right, that you see at low temperature. So basically, you have only one valley, right? No diode effect is observed. Right? This is very important because if you apply a magnetic field, you will see, and you will see at all angles. But if you do not apply a magnetic field, you will not see. And this is not happens at, let's say, 30 degrees. At 35 degrees, okay, there is some uncertainty, but definitely you can start to see at 40 degrees, which is the region where you may expect an interplane or interwine order between the first and the second harmonic contribution. And of course, you can imagine this as a dome, which gas then vanish once you get close to 45 degrees, because in that case, you have a dominant contribution of the second harmonic, which means only one valley again. So you do not have any more this coexistence between first and second harmonics. Okay, now, so this led me to think and to propose to some collaborator that maybe we could use this kind of multiple degenerate states at high temperature to think about a different transmon. And so the idea was to couple to this Josephson junction, which is the core of any superconducting qubit, to couple to this a new order parameter that we have artificially created to this a capacitor, which what makes the transmon so simple but also so beautiful, and we call this a flower mond. But basically, besides the name, that the story is that we think, okay, this is just theory, we think that by exploiting the inherent quantum nature that we have created at the interface by playing these complex oxides, we can create protection against charge noise-induced relaxation and quasi-particle-induced dissipation. Now, the challenge for our experimentalists is actually, okay, this is what we know how to do now. Now, how you do this, right? How you want to do all this? Because this is it's very complicated to make in a way that this guy is not having problem with it, right? So that his chemistry is not having problem with it. And it's very, very difficult. Now, the idea of course, we are not so smart in the sense that the idea of create cuprate qubit is a long idea and a old idea. And proposal for the suppression of the wave-based Josephson junction based on this momentum mismatch that you can create across the layers that should suppress the quasi-particles contribution has been proposed by Blatter, Yoff, and others in the past, from 1999, etc. Even there were proposals of 2D wave qubits coupled, which I was really impressed when I read this. And experimentally, however, we have been a little bit more encouraged by the work. Actually, it was done between Naples and Copenhagen of an experimental early realization of momentum mismatch with grain boundary IPCO junction, which indicated some sort of degenerate of the ground state. But here, in the case, the determinant disorder and fabrication complexity creates problem. Right? So, however, so this is the state. Now, the idea, to make it short, is that if you go from one valley to a double valley, you will have some set of states that will be degenerate, right? Two ground state degenerate, which will give you protection to the system. This is a phase diagram that puts together different parameters. I will not go much on that, but what I want to show is that, of course, this is theory again, I stress this about. You may have an exponential suppression of the charge-induced node if you manage to create the circuit. Now, what is the state of the experiment? Well, of course, there are other things that we can do with resonators, which are not necessarily related to superconducting technology. For example, we have tried recently to, this is unpublished results, we tried recently with Yuri Vol to design a superconducting resonators and basically stack with this cryogenic technology a flake. And we see a kind of good interface between the superconducting resonator and the BISCO. However, when you stack things on top, you necessarily create a little bit of strain. So this is definitely not a way to do van der Waals set of structures. But for very thick flakes, it's okay. And the idea is that we actually do see some coupling. This is the important part. So if you see basically the transmission spectrum of the resonators, okay, that you can see here, R1, R2, these are have different lambda. One is lambda 4, another is lambda 2. And then there is one with the BISCO. And you can see that the frequency in gigahertz shift and see somehow BISCO is having an impact on the overall circuit. So he's having some sort of torque, okay? And this coupling, it's not given from granted. Many 2D materials, they are not coupling so well, so it's not obvious. Now, what you can see is that the frequency change as a function of temperature for a normal superconducting resonator that you expect to follow BCS, right? And a TLS system, so a two-level states, right? So it does what it has to do. But for what concerns the BISCO, you see some sort of deviation, some sort of anomaly, and that goes as a function of temperature. Now, this seems to be that the TLS here are playing some role. However, you can believe me that some of the aspects that we have also measured, that I don't have it now, shows that only a two-level state description is not sufficient to describe the observed coupling with the superconducting resonator. So it's possible some other aspects of the BISCO are influencing the superconducting resonator. So, but for the future, what is my belief, and with these few slides I finish, what is my belief is that for the next generation, we needed to think a completely novel way to realize electrical contacts. So one time somebody told me that 90% of my job is to make electrical contacts, is to learn and understand how to make electrical contacts. I was feeling a little bit sad, humbled, but then I understood after several years that it's actually a very important thing and is not trivial at all. And so one thing that we are working now is to realize a wafer where we have silicon nitride, and with this silicon nitride, what we create is to create circuits on top. We use this PDMS stacking technology to basically stack, exfoliate, and print these circuits wherever we want. So we do not anymore do any evaporation, anything like that. We exfoliate, in this case, a flake, and on top of that, we realize electrical contact directly on the electrical paths of this membrane that we put on top. And so you can see that there is some sort of degradation here, 0.5 unit cell, between the electrical contact and the remaining part of the visco, but it's pretty good. And the idea is that you can start to use materials that are not only gold, that you can start to use electron beam lithography, you can start to use magnetic material, maybe you can also use atomic layer deposition to coat with 2D materials this membrane and create special contacts. So basically the point is that we can create, I wanted to entirely separate the circuit fabrication from the van der Waals materials fabrication. This has to be completely disentangled. And the results shows that we have an RTC for a, let's say, for a 3-unit cell sample, which is 10 nanometer, 12 nanometer of 91 Kelvin. Even after 10 days, we can measure all effect. The contact resistance is extremely low, 20 ohm. Doesn't change on the course of, let's say, 60 days. Right? And we can measure the effect. I will not go on this. But we can also apply to different materials. Right? And so this allows to do things that I think before were not possible. And so with this, I would like to lead you to the conclusion. So I hope that I convinced you that we are now able to engineer complexity and topological and strongly graded physics in one system in a wide temperature range. We want to advance the methodologies for the fabrication of artificial 2D complex quantum materials. And hopefully we want to produce a new generation of quantum circuit harnessing the unique quantum complexity created by the geometry of your system. Thank you.
Yeah, we have enough time for questions. Yes, Arindam.
Right. So I'm trying to understand what's the effect of the bulk of the crystal and the interface separately, because these are not monolayers, right? So you also have the bulk of the superconductors, which is not at the interface. So is there any effect of that in your experiments?
Laura, so I will start with theory and then I will tell experiments. In theory, they show that there should be, all the things that they predict for the monolayer should scale quite nicely for the finite flake. So that's not a big deal. From my point of view, it's actually a great thing that we are doing with flakes and not monolayer. First of all, the flake on top, all the other layer makes the contact. So you can imagine these twisted flakes, like that you have two monolayers touching to each other, and all the metallic part that or superconducting part that you have on top is making the contact. In fact, not only that, is that they make the contact. You see always that you get on the surface, let's say 1 unit cell or 0.5 unit cell of degradation. But this doesn't matter because it's amorphous, it's metallic. Then you have a superconductor, which is your contact. And the most important thing is, this is one of the reasons why we do this stacking very quickly, and is these two things, where they touch. But there is also another advantage that, for example, people that work on graphene, they do not have. When you have thickness, right, you have also elastic modulus, which is higher. So these are really slabs that you put on top of each other. They really stay like straight. And now, if, for example, with IDA, we are thinking about it, but if we want to move to monolayers, right, we will start to encounter all the problems that you find in graphene. So, for example, twist angular disorder in an extensive way. And with complex oxide that you have no stoichiometry system, right, could be interesting, but could be also a tragedy, right? Because the elasticity, you have to play with that, and it's very tough.
Right. And one last question on the reproducibility of the interface in terms of the critical current. I see the critical current falls, that's right, at around 45 degrees or so. But if you make large number of devices, what's the range of critical current that you see here?
Okay, so the 45 degrees, if you speak about really the 45 degrees, if you really speak about the 45 degrees or 44 point something, these are very difficult sample to make. So I would say that you have a chance 1/15 to make something like that. In fact, I try to say and to stress the point that if any technology or something that could be realized, I do not point to 45. I hope to this region of coexistence that is around 40 degrees, where we have a good compromise between minimum yield and minimization of detrimental disorder. So unfortunately, we have to compromise. So, but I would say that 45 degrees is interesting for, in principle, reason, and maybe also if you want to really to push the property of your system to the extreme, but already it would be a miracle to have a prototype. So I would say that the range is around, okay, 30 microampere or something like that, I remember, but it is the yield that the problem, I would say. So it's a bit annoying, yeah.
Yeah, Jeet.
Okay, mine is a very simple question. So in that picture on the right-hand side, you're showing like heterostructures where the bottom is flat and the top is corrugated. And somehow it looks like you're distinguishing the substrate from the deposited layer. But again, what would happen if you sort of, the top deposited layer is also on a firm substrate, whether by temperature treatment you could somehow propagate the strains to be evenly distributed?
Yes, so this modulation is something that I want to keep. So this modulation is intrinsic of the BISCO and is only along B stars. All the cuprates have this modulation along B stars, and some of them form paddles, right, of structural stripes. But only the BISCO forms this very long range wave. So what I do here is to try to imagine that we are here, and with the Scotch tape, instead of breaking these layers, we break, this is bismuth oxide and this is bismuth oxide. So we break this van der Waals gap, right? So it's exactly what you see here, but I have restacked it with an angle. So you see the modulation is only along B, is 1D, so you cannot see along A. So it's not, it gives a strange impression that there is a corrugation, but it's not. I don't know if I managed to convince you. I mean, if you look at the bulk crystal and you see how the modulation are in B and A, you will see that this is not given by the fact that we have created the structure, it's just that we have break these bonds and, you know, these van der Waals, yeah.
Any more questions, please?
Hello, hello. Yeah, very nice talk. So I have one question from the parabolic structure that you showed while making the qubits. So you mentioned there are 0.25, like 45-degree angle, there is like the single Cooper pair tunneling is suppressed because of the asymmetry. But in that case, how one is going to access the like qubit states if at all a qubit is formed, if the single Cooper pair tunneling is suppressed? So
Maybe can you rephrase it a little bit?
So, for example, if there is a qubit formation by twisting at 45 degrees, and it suppresses a single Cooper pair tunneling, but then if you have to change the qubit states or whatever, then in that case, like the suppression of Cooper pair tunneling, will it allow the changing? Like how one gets access to the states of the qubit?
Okay. So this is, I will not easily answer to this question. So we have written something about how to control the qubit, right? This is the question, how you want to control it, right? So there are possible protocols that one can envision, right? To how to, but at the moment, this is only, for example, we needed to learn about real measurements of capacitance. We need to know a lot of details to understand how we actually want to design control, right? So we can guess, there is a guess in, for example, in the paper we published. I'm not an expert of qubits, so not too much, I would say. I'm more material. So it's a complex question. It's not, we have not yet, as an experimentalist, I cannot give you a convincing answer. As a theorist, I will not dare. Yeah.
And just one more question. So is there a control on the thickness of the exfoliated flake? Like, can you control the thickness or?
No, it's a statistical process. Generally, we know that if we start from a large flake, if you exfoliate it, you will get two pieces, which suppose if you have a flake of 100 nanometer, maybe the two pieces will be 40 and 60, or 50-50, or 30 and 70, right? So there is not really a control on that of the way that you think about it.
Thank you.
If there are questions from our online participants, I request to just unmute and ask the question. Online participants. Okay. We don't hear anything, so let's thank Nicola one
Thank
more
you.
time for the very nice
Thank you,
talk.
thank
Thank you.